Page 100. Law of conservation of mass and energy. Recap. All changes in matter may be classified as physical changes, chemical changes, or nuclear changes. Section A. A physical change in matter involves a change in appearance only, such as size, shape, or state. Although the changed matter may look very different, no new substances are formed during a physical change. For example, when water changes from solid, such as ice, to a liquid or gas, which is water vapor, which is invisible, the water molecules themselves have not changed. Only their state of matter has changed, as the molecules gained kinetic energy. Section B. New substances are formed during a chemical change. Mixing materials together does not always produce a chemical change. Evidence must be found that at least one new substance with different properties has formed before it can be concluded that a chemical change has occurred. The starting substances are called the reactants. After they react with one another, one or more products results. The products have different properties than those of the reactants. A chemical equation represents the changes that take place during a chemical change. The chemical formulas of the reactants are written on the left of the equation, so left of the arrow. An arrow indicates the formation of a new material, which is called the products. The products are to the right of the arrow. The chemical formulas of the products are also on the right. Although changes occur on the molecular level, it is often possible to observe evidence that a chemical change is taking place. The clues to chemical change which are observable are production of a gas, such as bubbles, color change, formation of a precipitate, which is a solid, and temperature change. Also, an odor and the apparent disappearance of a reactant may be evidence of chemical change. When a new substance is formed, there has definitely been a chemical change. The two types of chemical reactions which result in temperature change are called exothermic and endothermic reactions. Energy is released during an exothermic reaction. The prefix "ex" means out, so heat is exiting this reaction. This happens because less energy is needed to break the bonds in the reactants than is given off when a new bond forms in the products. The excess energy is given out in the form of thermal energy, and the temperature increases. The burning of a fuel, oxygen combines with the fuel, is an exothermic reaction. Endothermic reactions require a continuous input of energy. The prefix "endo" means inside or within. So for endothermic reactions, energy needs to go in. Energy from the surroundings is taken in and used to break in the reactant's original bonds and form new bonds in the products. An endothermic reaction results in a decrease in temperature. For example, when a chemical cold pack is placed on a sprained ankle, thermal energy from the surroundings, the air and the ankle, is used by the chemicals in the cold pack. The ankle is cooled as a chemical change takes place in the cold pack. Section C. Chemical changes are often affected by the surface area to volume ratio of the materials involved in the change. For instance, when a solid reacts with a liquid, the smaller the particles of a solid, the faster the reaction will take place. This is because smaller particles expose more surface area to the liquid. Section D. The law of conservation of mass states that no matter how substances within a closed system are changed, the total mass of the system remains unchanged. When a chemical or a physical change takes place and no substances, gases, are allowed to escape, the mass of the reactants will be exactly the same as the mass of the products. Matter is not created or destroyed during the change. A number written in front of a chemical formula is called a coefficient. It tells the number of molecules involved in the reaction. When there is only one molecule, the number 1 is not written, but understood. So in this example, Cu does not have a number written in front of it, so we just assume that it has 1. Whereas here, there's a 2 in front of the N, so we then know that there are 2 nitrogens. Coefficients show the proportion of the molecules on each side of the equation. In the example above, 1 molecule of copper sulfate requires 2 molecules of ammonium hydroxide molecules to produce 1 molecule of ammonium sulfate and 1 molecule of copper hydroxide. In a balanced chemical equation, the total number of each type of atom on the left of the equation, the reactants, must equal the total number of that same type of atom on the right side, the products. So if we look at this example here, and we count the number of atoms, we'll see that we'll have the same amount of each atom on both sides of the equation. So the reactants has 1 copper, 1 sulfur, 6 oxygens, 2 nitrogens, and 10 hydrogens. The same can be said for the products. The numbers match up. The numbers of atoms of each element in the reactants on the left of the equation is the same as the number of atoms of each element in the products on the right. This shows that matter has not been created or destroyed during the chemical change. To find the number of oxygen molecules on both sides of the equation, reactants, there's 1 molecule of CuSO4, which has 4 atoms of oxygen, because that 4 is distributed to the O. So there are 4 oxygen atoms. There are 2 molecules of NH4OH, and each molecule has 1 atom of oxygen. There's a total of 6 atoms of oxygen in the reactants. So once again, we have 4 here, and then 2 here, because this large 2, this coefficient, is distributed to the N, to the H, to the O, and to the other H. So since this 2 is distributed to the O, there's 2 oxygens here, plus the 4 here. So that's a total of 6 oxygens. On the product side, we see that there are 4 oxygens here. And once again, this 2 is distributed inside of the parentheses. So 2 go to the oxygen, 2 go to the hydrogen. So there are 2 oxygens here, 4 here, so when added together, they equal a total of 6. Products. There is 1 atom of NH4, 2SO4, and has 4 atoms of oxygen. There is 1 molecule of CuOH2, and it has 2 atoms of oxygen. The total number of oxygen atoms in the products is 6. A balanced equation has the same number of each type of atom on both the reactant and product side of the equation. The steps for writing a balanced equation are: 1. Write the chemical formulas of the reactants and the products. Place an arrow between them. This arrow is read as yields. Step 2. Check the equation for the number of each kind of atom on both sides. In this example, the number of oxygen atoms in the reactants is not equal to the number of oxygen atoms in the product. So if we look here, there's 1 magnesium, 2 oxygens. Whereas on the product side, there's 1 magnesium and only 1 oxygen. Step 3. Choose coefficients, that's numbers in front of letters. Choose coefficients that balance the equation. The reactants must have the same number of each type of atom as the products. Add coefficients so that the total number of each type of atom is the same on the right as it is on the left. Remember that the ratio of atoms within a compound does not change, so subscripts must not be changed. So over here we have 2 magnesiums, and on the right we also have 2 magnesiums. On the left we have 2 oxygens, and on the right we also have 2 oxygens, since that 2 is distributed to the magnesium and the oxygen. So right now we have a balanced equation. Section E. Some atoms undergo changes in the nuclei of their atoms. One characteristic of nuclear changes is the release of a large amount of energy from a small amount of matter. Nuclear fission is the process which a large nucleus of an atom, such as uranium, splits into 2 smaller nuclei, and energy is released. The new nuclei are different elements. Uranium becomes barium, and krypton. Nuclear fusion is the process by which two or more nuclei have small masses and they combine or fuse to form a larger nucleus. A large amount of energy is released when this is done. This process takes place at very high temperatures. For example, the fusion of hydrogen into helium releases huge amounts of energy and is the main source of stars, including the sun. Hydrogen bombs use the energy of fusion. Fusion is difficult to produce artificially and is very difficult to control. The use of fusion as a controllable energy source on Earth is still in its experimental stages. This ends the Law of Conservation of Mass and Energy section.